2 billion tons of waste are generated across the planet every single year. One can notice that glass constitutes more than 20% of this massive volume. Millions of glass bottles possess a molecular structure so stable, they can remain in landfills for over 1 million years without undergoing natural decomposition. This creates an ever-growing accumulation of refuse that occupies vast territories. Why is this material considered a crisis if it is fundamentally inert? It seems like a simple problem of storage, but in reality, the sheer volume of non-decaying containers threatens to overwhelm modern waste management systems. Fortunately, glass possesses a unique physical property that allows it to be recycled an infinite number of times without any loss of its original structural quality or purity. Industrial facilities now process hundreds of tons of glass every 24 hours to return them to the manufacturing cycle. But this is just the beginning.
Automated systems receive thousands of broken and contaminated fragments from urban collection points. One can notice how the equipment gradually sorts these messy shards into distinct categories based on their chemical composition and color. This transformation from jagged waste into polished, transparent containers follows a precise technical sequence that is only gaining momentum as global demand for sustainable materials increases. The equipment operates ceaselessly to ensure that every fragment is cleaned of labels, adhesives, and organic residues. It is visible how the glass moves along conveyors toward high-temperature furnaces where the material will lose its solid form. The journey of this material represents one of the most efficient closed-loop processes currently utilized in heavy industry. Everything only gets more complicated as the glass enters the melting phase, where temperatures must be maintained with absolute consistency. This complex recovery operation ensures that glass remains one of the most sustainable resources available for industrial use. The material is ready to move to the next processing phase without haste. 10 to 20 cents is the typical refund value assigned to a single empty glass bottle within advanced collection systems. The entire recycling cycle relies fundamentally on a continuous and predictable supply of used containers. Why is the initial collection phase so critical to the success of the plant? In daily life, empty soda or beer bottles frequently end up mixed with general household refuse, a situation that renders the subsequent sorting process both expensive and technically difficult. But in various European nations, a systematic solution addresses this inefficiency directly at the point of origin. Automated bottle return machines are positioned throughout city streets and inside supermarkets to intercept glass before it enters the waste stream. It only looks obvious to dispose of glass as trash, but in reality, these reverse vending machines transform a finished beverage container into a financial asset immediately. Consumers place an empty bottle into the intake aperture, where sensors perform a digital scan to identify and sort the material. The equipment gradually accumulates a pre-sorted inventory while issuing a small cash refund to the user. But this is just the beginning. This specific economic incentive motivates citizens to participate in the collection process, ensuring that factories receive raw material that is already clean and consistent in quality. The process is only gaining momentum. Specialized logistics companies deploy heavy trucks to these collection points once the internal storage of the vending machines reaches capacity. Forklifts are used to hoist large plastic bins, each containing several thousand glass bottles, onto the flatbeds of the vehicles. One can notice how the hydraulic arms of the forklift stabilize the weight during the lift. A single full-size transport truck can accommodate between 20,000 and 30,000 bottles during a single transit. This volume translates to a total weight of approximately 10 to 12 tons of material per load. Trucks packed with these bins depart from urban centers and navigate toward the specialized recycling facility. It gets more complex further on. The drivers maneuver their vehicles into massive storage bays upon arrival at the plant. One can notice how the trucks back into position with a slow tilt of the bed or a release of the bin locks. The equipment gradually discharges the load, causing a massive cascade of containers to tumble onto the floor of the bay. In a matter of minutes, the storage area fills with mountains of glass that shimmer as they catch the overhead lighting. Green, brown, and clear glass fragments accumulate in large, distinct piles across the facility floor. The material is now ready to move to the next processing phase without haste. Tens of thousands of glass fragments form towering piles that serve as the fundamental starting point for the entire industrial recycling chain. These massive mounds of discarded material represent a steady supply of raw resources awaiting meticulous cleaning and mechanical crushing. Why do massive loaders prioritize these specific piles for the initial stage of processing? It seems simple to just move material, but in reality, the loaders must ensure a consistent flow to prevent the production line from stalling. The loaders maneuver through the yard and scoop up thousands of kilograms of glass in a single motion of their hydraulic buckets. Massive loaders drive up to the towering piles to kick off the recycling process. The glass is eventually dumped into the plant's feed hopper with a thunderous crash, sending a sharp cascade of multicolored shards sliding down the angled steel chute. Instantly, the heavy steel conveyor begins its rhythmic movement, carrying the jagged stream of glass mixed with dirt and sand deep into the interior of the facility. One can notice how the belt vibrates under the weight of the raw material as it enters the darkness of the processing hall. The first stop is the vibrating screen, where powerful high-frequency shakes separate out fine dust, grit, and microscopic particles from the larger fragments. After this mechanical stage, the glass appears significantly cleaner to the eye, but larger contaminants that automated sensors cannot easily detect still remain embedded in the flow. But this is just the beginning. Along the moving conveyor, specialized workers stand positioned at fixed intervals, their hands moving with practiced speed. They carefully pull out scraps of paper, tangled plastics, and any other foreign objects that do not belong in the furnace. This calculated blend of coarse mechanical screening and precise human intervention produces a much cleaner batch of material ready for the subsequent stage of the recycling journey. It gets more complex further on. Why are metallic elements still hidden within that pile of broken glass despite the manual sorting? One might assume the workers could remove everything by hand. However, thousands of small bottle caps are often buried deep within the glass stream, requiring a more specialized approach for extraction. Luckily, most of these caps are manufactured from ferrous metals, meaning they can be pulled out with high-powered magnetic separators. The physical principle is simple, as the equipment gradually draws all metallic debris toward the magnetized drum. The strong magnetic field grips the bits of steel and pulls them upward while the glass remains unaffected, continuing its steady path down the conveyor belt. Thanks to the integration of this electromagnetic step, the glass is now approximately 80% clean and significantly closer to its ultimate journey of rebirth. Once the majority of these contaminants have been successfully removed, the glass moves forward to the next phase of the process. The material leaves the separator, transitioning into a calm stage of the production line. 100% of the contaminants must be eliminated before the glass transitions to the next technical phase, which involves grinding the material into cullet. Why is the reduction of particle size so critical for the efficiency of the entire plant? The answer lies in thermal physics, as smaller fragments require significantly less heat to transition into a liquid state than raw mineral components. But in reality, achieving this uniform consistency requires a violent mechanical intervention within the hammer mill. High-speed steel hammers rotate within a massive housing, striking the larger pieces of glass repeatedly with immense kinetic force. One can notice how the impact shatters the shards into progressively smaller fragments until only tiny granular pieces remain. Any fragments that exceed the specified technical dimensions are automatically intercepted by sensors and rerouted back into the grinding chamber for a secondary cycle. This closed-loop system ensures that the resulting stream of material is perfectly uniform. The process is only gaining momentum. The glass is transformed into cullet, consisting of fine, sparkling particles that resemble synthetic sand in both texture and appearance. Because the surface area is so vastly increased, this cullet melts much more rapidly inside the furnace. This acceleration saves up to 40% of the energy required compared to processing raw materials such as sand or limestone. At first glance, the material appears ready, but microscopic impurities still linger on the surfaces of the grains. The camera glides along the transport line as the cullet enters a high-velocity suction system. A powerful stream of compressed air blasts through the falling material, stripping away every remaining fragment of paper labels and adhesive residue. It is visible how the lightweight debris is blown into a collection duct, leaving the glass substrate even cleaner than before. Transition to the next level. Lasers now take over the monitoring of the production flow within the optical sorting system. As the glass cascades downward in a shimmering waterfall, high-frequency sensors scan tens of thousands of individual fragments every 60 seconds. Why is such extreme precision necessary at this specific moment? If even a single ceramic shard or a fragment of the wrong shade remains, it will compromise the structural integrity and clarity of the final product. The system instantly fires a millisecond puff of air the moment it identifies a brown fragment, a green shard, or a piece of stray ceramic. These rejected particles are shot into a separate diversion stream with nearly unbelievable speed. The equipment gradually refines the batch until it reaches a state of perfect color accuracy. The tiny glass particles move along the conveyor belt toward the final distribution point. Everything only gets more complicated as the volume of material increases. The cullet is directed into specific storage sectors, each strictly divided by color to prevent any cross-contamination. Massive stockpiles of sorted material gradually accumulate in the holding area, awaiting the next thermal transition. The glass remains in these designated zones until it is ready to be loaded into the melting chambers for the production of brand new bottles. Thus, the material reaches the standard required for the final stage of its transformation. 1,250 degrees Celsius is the minimum temperature reached within the massive gas-fired furnaces during the initial heating phase. This thermal intensity exceeds the heat of volcanic lava and serves as the primary catalyst for molecular transformation. Why must the cullet be combined with specific mineral additives before entering this environment? Pure silica sand remains the foundational component for structural clarity, but it requires chemical assistance to become workable. Soda ash, or sodium carbonate, is introduced to the batch to effectively lower the melting point, which optimizes energy expenditure throughout the entire thermal cycle. Limestone enters the mixture to provide necessary structural reinforcement and long-term chemical stability for the finished glass. Manufacturers occasionally integrate dolomite, alumina, or various metal oxides to precisely calibrate the final color and physical properties of the melt. However, the recycled cullet remains the most critical ingredient in the technical formula. It typically constitutes between 20 and 70% of the total batch weight. This high concentration allows the melt to flow with increased speed and reduces total energy consumption by 40% when compared to processing virgin raw materials alone. It only looks obvious that cullet is a filler, but in reality, increasing its volume by just 10% reduces energy needs by 3% and significantly lowers carbon dioxide emissions. The process is only gaining momentum. Technicians carefully monitor the distribution as the mixture is fed into specialized crucibles after being blended according to predetermined industrial formulas. Inside the facility, the environment undergoes a radical change. Workers are required to wear heavy fireproof suits and thick protective gloves because the ambient heat reaches nearly 3,000 degrees. One can notice how the air shimmers with thermal distortion as the equipment gradually moves the containers into position. Once the raw ingredients achieve initial stabilization, the mouth of each crucible is sealed to trap the extreme heat and regulate the melting kinetics. Transition to the next level. 24 hours of continuous heating completely alters the physical state of the silica. The material loses its granular form and begins to flow with the thick consistency of molten rock. A brilliant, incandescent glow becomes visible at the base of the furnace, signaling the presence of liquid glass in a dense and shining state. At this stage, the substance has attained the exact viscosity required for high-precision forming. For the subsequent 5 hours, the glass is held in this liquid state to allow any trapped gases to migrate to the surface and escape. One can notice the slag and bubbles dissipating, which ensures the highest possible purity levels in the structural mass. The molten glass then flows into a spinner to begin its mechanical shaping. Thousands of tiny holes in the walls of a rapidly rotating spinner allow the molten glass to be extruded as it reaches the final stage of purity. The centrifugal force shoots the material outward at extremely high speeds to form ultrafine fibers. A vertical stream of hot air blows downward with constant pressure to stretch these strands, while separate channels of compressed air provide cooling and control over the exact fiber length. Why is the thermal management of these fibers so critical during the spinning phase? The initial cooling determines the structural integrity of the glass. A primary spray ring utilizes only pure water to lower the temperature before a secondary ring coats the fibers with an exclusive formaldehyde-free biobinder. One can notice how the glass fibers are collected within a specialized forming chamber and distributed across a moving conveyor belt to create a continuous mat. But this is just the beginning. A cross-distribution system moves back and forth with mechanical precision to ensure that the density remains uniform across the entire surface of the material. The freshly spun fiberglass appears naturally off-white, characterized by a light and fluffy texture as it travels along the line. It seems simple to maintain this color, but in reality, the visual transformation depends entirely on the chemical reaction of the additives. A clear liquid binder is sprayed onto the fibers, initially preserving the white appearance of the mat before it enters the next thermal zone. The material undergoes a distinct color shift as it passes through the high-temperature curing oven. The binder hardens and turns the insulation yellow, orange, or pink, with the specific hue determined by the chemical formula used in that batch. The process is only gaining momentum. Heavy rollers descend upon the fiberglass wool to compress the soft, airy mat into a firm block with a strictly calibrated thickness. This mechanical pressure locks the individual fibers together to increase the density of the material. It is visible how the compact block then moves into the cutting line, where rotating blades slice the wool into panels of exact dimensions. Everything only gets more complicated as sensors and guides monitor the movement to ensure every sheet adheres to international building standards. The finished panels are wrapped in a protective film and sealed tightly to prevent any intrusion of moisture or physical damage during subsequent logistics. The equipment gradually aligns the bundles for the final stages of handling. Forklifts lift and stack the packages onto pallets, which are then transferred into the cargo holds of trucks for nationwide distribution. In the United States, the pink fiberglass insulation produced by Owens Corning occupies the majority of the market and has evolved into their signature industrial aesthetic. The company moved to trademark the specific pink color, establishing a legal right to its exclusive use in the industry. The material is ready to move to the next processing phase without haste. 1,400 degrees is the maximum temperature that molds manufactured from cast iron or alloy steel must withstand during the glass shaping phase. Why is the creation of these molds considered a separate engineering discipline? At first glance, it seems simple to pour liquid into a shape, but in reality, the mold determines the structural integrity and technical precision of the final product. Engineers utilize advanced computer-aided design software to calculate every line, dimension, and thickness. Transition to the next level. From these digital blueprints, the physical molds are produced and meticulously prepared to receive the molten material. These heavy units are then installed into the double-blow production line. This method remains one of the most reliable and widely used systems for the mass production of hollow glass items, ranging from pharmaceutical containers to food jars. One can notice how the equipment remains perfectly aligned during the installation of these cast iron components. The forming process begins when molten glass segments, known as gobs, are dropped into the initial blank mold. These gobs are sheared from a continuous stream of liquid glass and maintain a temperature of approximately 1,100 degrees. It is visible how the glass maintains a specific viscosity to ensure smooth and consistent shaping. But this is just the beginning. Inside the preliminary mold, a jet of high-pressure compressed air is blown in from the top. This force pushes the hot glass outward against the inner walls to create a parison, which is a hollow, bubble-like structure featuring a narrow neck. The process is only gaining momentum. The parison, still glowing with intense thermal energy, is gently moved to the final mold located only a few inches away on the same production line. Here, a second burst of compressed air is injected directly into the center of the hollow structure. This action stretches the softened glass until it presses tightly against every contour and fine detail of the inner cavity. It only looks obvious that the glass takes its form instantly, but in reality, every valve and sensor in the system is synchronized down to 1,000th of a second. Everything only gets more complicated as the production volume increases. This extreme level of precision allows for the manufacture of hundreds of thousands of units every 24 hours. Each bottle emerges nearly identical and flawless. One can notice the deep red heat radiating from the glass as it is released from the mold, shimmering like glowing metal rods in the industrial environment. Robotic arms move with seamless programmed precision to interact with the finished shapes. Each bottle is lifted with care and placed onto the conveyor belt for transport. The equipment gradually transitions the product away from the heat. The entire sequence unfolds in silence and perfect synchronization. Thus, the glass reaches the standard ready for the further stage. 1,200 degrees is roughly the temperature of the glass as it begins its movement towards stabilization. Why is the cooling process conducted with such extreme deliberation inside the long yellow tunnel? A sudden drop in temperature would cause the internal structure of the material to shatter instantly under thermal stress. The conveyor belt moves at a steady pace, guiding the newly formed containers whose bases still radiate a visible dull orange glow. This is not a rapid transition as the glass requires time time to settle its molecular bonds safely without the risk of spontaneous fracture. The process is only gaining momentum. It seems simple to just let the glass sit, but in reality, the tunnel environment is strictly regulated to lower the heat little by little. One can notice how the shimmer of heat waves gradually dissipates as the bottles travel through the enclosure. This critical cooling phase possesses its own rhythm, lasting for several minutes and occasionally extending to tens of minutes depending on the thickness of the walls. It does not end at this stage. High-speed cameras and an array of optical sensors wait at the exit of the cooling zone to examine the output in real time. The equipment gradually scans every square millimeter of the transparent surface for imperfections. Every detail undergoes verification, and the system is programmed to identify cracks, bubbles, scratches, or even a tiny warp in the geometry. Transition to the next level occurs the moment a defect is flagged, causing the automated arm to pull the compromised bottle off the production line immediately. Why must the mouth of the bottle undergo a separate, specialized examination? The seal of the final product depends entirely on the structural integrity of the finish. Precision automated systems rotate each individual unit, while mechanical probes and optical sensors work in tandem to find flaws. They seek out chipped edges, fine cracks, or the smallest deviation in the required dimensions. It is visible how the sensors sweep over the glass threads with millisecond frequency. Only the containers that satisfy this strict dimensional check are permitted to advance toward the packaging department. Everything only gets more complicated as the bottles enter the palletizing section. Robotic systems take full charge here, operating with a level of accuracy and uniformity that human hands could not replicate. A specialized clamp mechanism equipped with a series of suction cups lowers from a heavy gantry to grip an entire row of glass. One can notice the hiss of pneumatic valves as the machine lifts the weight and sets the layer carefully onto the wooden pallet. But this is just the beginning of the logistical preparation. To protect the fragile surfaces against impact during future handling, the system places a protective sheet between every horizontal layer. When the stack reaches its prescribed height, an automated wrapper rotates around the pallet, securing the glass in layers of industrial film. A label printer applies a unique code that corresponds to the specific production batch for full traceability. The glass pallets are eventually moved into the storage warehouse, where they are neatly stacked in towering rows. From this point, the containers are prepared for shipment across the globe to be filled and utilized in daily life. The molten material has transitioned into a stable, finished form, ready for the final leg of its journey. Thus, the steel-like precision of the glassworks concludes this phase, opening the road to distribution. 100% of glass can be recycled without any loss in quality or chemical purity during the thermal transformation. Why is this closed-loop process considered the pinnacle of modern resource management? It seems simple to merely melt down old shards, but in reality, this cycle prevents the depletion of natural sand reserves and reduces industrial energy consumption by nearly 40%. This recovery system ensures that every fragment processed in the furnace retains its structural integrity for an infinite number of cycles. The process is only gaining momentum. One can notice how the automated sorting lines transition the raw cullet into the high-temperature melting chambers, where the material reaches its liquid state once again. The camera glides along the conveyor as distinct colors are separated with millisecond precision by optical sensors. It gets more complex further on. Modern technology transforms discarded containers into high-grade industrial resources through a sequence of mechanical crushing and intense thermal purification. Because the molecular structure of glass does not degrade, it remains a permanent asset within the manufacturing chain rather than a terminal waste product. One can notice the brilliant glow of the molten mass as it pours into new molds at temperatures exceeding 2,700 degrees. This industrial rebirth cycle provides a technical template for sustainable production, where the concept of disposal is replaced by total reclamation. The material consistently returns to the production line, maintaining the same transparency and strength it possessed during its initial creation. From here, the finished glass products move toward the cooling tunnels to stabilize their internal stresses. Thus ends one of the key stages of glass production, as the material is prepared to re-enter the economy without haste.